This is how to fine-tune a large language model so you can get it to do exactly what you want, but for cheap. There are a ton of great LLMs out there and most of them work pretty well, but they're not all that cheap. Look at this. You need to pay for the privilege. What if we could get it fine-tuned for this and running for this? And what happens when those big LLMs don't quite work? This happens more than you think. It's usually when you've gone down a really specific rabbit hole on a niche topic and no matter how good that LLM is, it loses the plot. Little like this. What if you could apply a knowledge cartridge to that LLM and inject the right knowledge for specific use cases? This is what fine-tuning aims to do. But full fine-tuning is costly and it takes time. LoRA, a low-rank adaptation, is like plugging in a new game cartridge. We're able to add in the specific knowledge that we need without having to go through the extensive cost or time of retraining all of the existing LLM parameters. And by running a quantized version of it, we can get it to run fast on any old laptop, like my MacBook here. I'm gonna take you through a complete end-to-end walkthrough on a custom training dataset in under 60 minutes. But do I need to use a massive LLM to do this? And what if you only have PDFs or text or code? How do you use that for training? And are there specific training parameters that AI engineering pros use? I went down the rabbit hole with this and you'll see a little later on that I did well over 15 training runs to get this workflow developed. But it means that it's ultra straightforward to train your own LoRA now. On this positive note, I'm gonna break this down into 7 stages. First up, how bad is the LLM hallucinating? So my first job in tech was actually as a technology consultant focused on a tool called TM1. Now it's a little bit of software that's mainly used for finance teams. Basically, it's like Excel on steroids. Now, I want to see how much I can teach an LLM about TM1. Now, keep in mind, just because I'm using this data doesn't mean you need to. Later on, I'm going to show you how to use your own data. So what exactly makes LoRA so unique? Well, imagine full fine-tuning looks like this. In order to fine-tune the model, we need to update the weights in this white matrix. This parameter update is updated by this pink matrix. Note they have the same size. If we take an example which has 8 rows and 8 columns of weights, that means 64 parameters to update. LoRA, on the other hand, is usually represented like this. It's made up of 2 weight matrices for every one you choose to tune, the lower matrix A and the upper matrix B. A key hyperparameter in LoRA is the rank of the matrix. This basically dictates how large the adapter to the LLM will be. Higher rank equals more parameters to update. Let's say we set the rank for this adapter to 2. This will give us matrix A, which has 2 rows and 8 columns, so 16 parameters to update, and matrix B, which has 8 rows and 2 columns, also 16 parameters to update. That's 32 parameters to update in total. But there's a problem. The dimensions of the weight need to match the original white pre-trained weights in order to add them together. And remember, these are 8 by 8. If we look at the dimensions of A and B here, they don't quite match. How do we fix this? Well, if you multiply matrix B by matrix A, you end up with matrix BA, which just so happens to have 8 rows and 8 columns, a match for the original pre-trained weights. If you then add these weights to the original pre-trained weights, you're able to get the benefit of a fine-tuned adapter with half the parameter updates of a full fine-tuning run. Kind of realize later on though that if you make rank too high, it can end up being more costly than a full fine-tuning run. So setting rank to an appropriate value is important. Right, so first up, how much does this LLM actually know about TM1? In order to estimate that, we're gonna use a couple of baseline questions that I've gone and predefined. The first question is, what is a pick list in TM1? And the answer to that is a list of valid values for a specific element or a cube cell. So it's effectively a drop down. Second question, what is the minimum number of dimensions for a cube in TM1? In this case, it is 2. I think this one's going to be really interesting, right? Because a cube would typically have 3 dimensions. So we'll see if we can train that into the LLM. The third question, how do I create a dimension? So you can open up a dimension editor, insert different elements. So basically allows us to define a perspective inside of our cube. Now, our fourth question, this one's a little bit airy-fairy, but we'll give it a crack. What are the core advantages of TM1? Runs in memory, it's extremely quick, you're able to model complex business logic, you can integrate with ERPs, CRMs, APIs, so on and so forth. Now, I'm gonna use a pretty small LLM for this, namely Llama 3.21b. This means that it's small, fast, and can be updated for pretty cheap. I think it works out costing like 50 cents to $2 to fine tune. So then you can run it locally on your machine, which means it's kind of free. Now, I'm gonna run this using Langflow and Ollama here. You can install it by running this command in your terminal and run it by running this command. Right, let's run through the baseline questions. So I'm gonna open up the playground and we can create a new chat. Just keep in mind, I'm currently running this on Llama 3.21b. So this is a completely unfine-tuned model. So if we go and also I wanna say that I'm using top K is equal to 1, which basically means that we should be using greedy decoding. So not a hell of a lot of creativity. So I'm gonna open up the playground and let's open or run our first prompt. So what is a pick list in TM1? If we go and run that, So we've got a set of responses. So in TM1, tallyman1, a pick list is a set of predefined values or options that can be selected from within a form, report, or other business object. It's essentially a predefined set of choices that can be used to narrow down a selection. This actually isn't too bad. In TM1, pick lists are often used to restrict values that can be entered into a field. Doesn't look too bad. So that one looks okay. All right, what about our second prompt? So what is the minimum number of dimensions for a cube in TM1? So let's paste that in and see. So the answer to this should be 2. And it looks like we've got something which could potentially be a hallucination. So in TM-1, cube is represented by 4 points and each point is 3 coordinates. Now this does not look right. Okay, so we're going to take this as a hallucination. Okay, all right, so what about our third prompt? In TM1, how do we create a dimension? All right, to create a dimension in Microsoft Dynamics 365, all right, straight away, we've already got a hallucination because I've asked it for TM1, we've gone and referenced another system. Okay, so we've definitely got a hallucination there. So not performing all that great so far. And then what are the core advantages in TM1? So I mean, this one's a little bit generic, but ideally it should be something along the lines of data is stored inside of memory. Okay, improved decision quality, enhanced collaboration. I mean, this could be just about any system really. Integration with other systems, ERP, CRM, that looks pretty good. Okay, so those are our baselines. So we've established baseline performance, and you can see here that it's not performing all that well. How do we fix that? Well, we need to get our custom data set and take it from this to this, so we can begin training. This brings us to step 2, synthetic data generation. All right, so how do we improve this? Well, we need to go on ahead and get some data. So I've got this file here called tm1_dg_developer. You get the idea, it's quite a long title, but basically this has a bunch of information relating to the system that we're trying to teach our LLM about. So how do we actually get this into a format where we can actually go and convert it into an instruction tuning data set? Well, this is where Docling comes in. I'm going to go on ahead and create a new file and I'm going to call it syntheticdatageneration.py. This is where we're going to begin to generate our data. In order to use Docling, we're going to need to install it. So how do we do that? Well, we can run uv add Docling at our terminal. While we're at it, we're also going to install Light LLM and Colorama. Light LLM is going to allow us to hit our LLMs for generation, and Colorama is going to give us terminal formatting. So I'm going to use the Docling document converter to go on ahead and load up our PDF. So I'm going to bring in the document converter. I'm also going to bring in the hybrid chunker. This is going to allow us to segment our document into a number of different chunks. So I'm also going to bring in Colorama just because it makes stuff look quite pretty. So then we want to go on ahead and actually do something. So if name is equal to main, then what we're going to do is create a new instance of our document converter. We're then going to load in that document that I just showed you, so that PDF. But this is where you might be able to sub in, or this is where you definitely are able to sub in your own documents if you wanted to go and create your own instruction tuning data set. This is going to return back a document, which we are then going to pass through to our hybrid chunker. So that's going to give us some nice approachable chunks, which we can then loop through to go on ahead and create our instruction tuning data set. We're then going to create a data set temporary placeholder. So this is where I'm going to pass through all of my JSON objects once we've actually gone and created the data set. But for now, what we're going to do is loop through each one of these chunks. So we're first up going to print out the raw chunk in and of itself. And I'm specifically just going to print out the first 300 characters so we don't blow out our terminal. And then what I want to do is use the contextualize method from Docling. So this is actually going to append almost like a subject matter to the top of each one of these chunks. So we actually get a little bit of context as to what that chunk is about. To that, we'll pass through our chunk and then we're going to print out our contextualized chunk. So we have the difference between our raw chunk and the one that has some context. So you'll be able to see the difference. The raw chunk will be printed out in yellow and the contextualized chunk will be printed out in light magenta. To go on ahead and run this, I'm just going to open up my terminal again, and I'm going to run this particular file here. So to do that, I can run uv run syntheticdatageneration.py. Now, ideally, we should be able to see the difference between our chunks. Remember, we're going to have yellow chunks and light magenta chunks. Let's give this a sec to go and run. And take a look, we've got our raw chunks and our contextualized chunks. So if you actually take a look, let's take a look at this one here. So you can see our raw text is you can roll up low-level numeric data such as cells and units in several ways, so on and so forth. But with our contextualized chunks, we've actually got a topic which has been appended. So over here, you can see that it says creating multiple roll-ups in a dimension. Now, if we go and take a look at this one, it's to do with weight factors. And you can see by using the contextualized method or the contextualized chunks, we've actually got those appended. But we've now got some nice chunks which we can now begin to loop through to go and create our synthetic data. How do we take what we've just gone and built using Docling and convert this into a synthetic data set? Well, we're going to need a larger LLM to be able to go and distill this knowledge down. So we're going to set this up, and specifically we're going to set it up so that it specifically returns back a dictionary or a format which we're able to use for instruction tuning. So I'm going to import a bunch of stuff from JSON typing Pydantic, and then I'm going to bring in the completion method from Light LLM again. And I'm also going to bring in a generated prompt, and specifically a prompt template. So I'm just going to bring this in here. So we're going to generated prompt.py, and I'm going to grab this from one that I created earlier. And this is our prompt template. So basically, this is just going to take in a data chunk, which we're going to get from Docling, and the number of instructions that we want to generate. And this should ideally return back some instruction tuning data sets. Okay, let's get back to writing our code. So we are then going to create a record class, which is then going to return two objects, a question as well as an answer. So this is going to form our instruction data set, but we're not necessarily going to just return one instruction. So we actually want to return a number of different instructions. So we're going to return back a generated object, which is going to have a list of these instruction pairs. Cool. So now what we want to go and do is create another LLM call method similar to the one that we created before when we were just testing it out. This is going to take in a data chunk as well as the number of records that we want to generate, and it's going to return a dictionary. So this is all pretty much straightforward. You've seen this before. The only difference is that we're now using Qwen 2.514b, so a larger LLM model rather than our small Ollama model. Again, we're going to specify our role as well as our content, and this is going to take in our prompt template, which we've just imported from over there, and it's going to take in our data chunk and the number of records that we want to go ahead and create. Then we're going to set stream equal to true. We're going to specify our options. We're going to set the number of predictions equal to 2000 tokens. But the core difference is that we're also going to specify a response format, which is going to come from our response object here. So it should return a list of question and answer pairs. And we can do that by passing through our response.model JSON schema object over there. Perfect. And then what we're going to do is we're going to append all of those records, and we are going to go on ahead and print them out. So you're able to see those as well. So ideally, this should allow you to see the instruction pairs as they're being generated. And we're going to return our JSON object as well. Now, what we need to do though is we're going to comment this out because we're going to run our LLM call first with one example so you can see it. And to do that, first up, I'm going to create an example data chunk, which is going to take in a passage of string. We'll come back to this in a second. And that example data chunk is going to get passed through to our LLM call. So ideally, this example data chunk here is going to reference our data object that you see here in this particular function. Now, our example data chunk, well, I'm just going to copy this segment of this Wikipedia article, and we're going to paste this over here. And this should allow us to use this data chunk as our instruction tuning dataset reference, right? So this is effectively going to represent a chunk of data that we're going to use to generate an instruction dataset. So let's go on ahead and run this. So I'm going to clear our terminal, and we're going to run uv run synthetic data generation.py. And this should give us a result. So ideally what we're looking to see is some blue generated text, which represents our instruction tuning dataset for Nikola Tesla. And take a look, it's beginning to generate. So you can see the first generated question is who is Nikola Tesla or Nikola Tesla? And we've got our response, what is Tesla's nationality? And we've got our response there. Where did Nikola Tesla receive his education? And that response is here. And what significant work did Tesla do before immigrating to the United States, before moving to America? You can see that response there. And how did Nikola Tesla contribute to the AC electricity system? And that answer is right there. Now, what would happen if we did this on our documentation that we've loaded up using Docling and brought that together? Let's do exactly that. So first up, we are going to go on ahead and delete our example data chunk. Then we're going to uncomment the code that we previously had to generate our enriched text chunks. We're then going to go on ahead and pass each one of those chunks to our LLM call. And then we're going to pass through each one of those instruction data sets, and we're going to append it to our overall data set that we initially created up here. So this means that we're going to have it stored in a single object. So we're going to store the instruction data set itself, so the question and answer pair that we created previously, as well as the context. So we can come back and use that. And I'll come back to that a little bit later. And then all we're going to do is we are going to dump it out as a JSON object called tm1data.json. We're going to set that as right, and we are going to dump it out. Now, if we go on ahead and run this by, again, running uv Run synthetic data generation. This is going to generate our synthetic data, but this time it's going to be for our documentation PDF. So here you can see that we've got our raw text and our contextualized text. And as soon as we start to see the blue text, that's our generated instruction pair. And take a look. What is discussed in the main topic, or what is the main topic discussed in chapter 1? And we've got an answer. And now it's going to do that for each and every chunk. This is the advantage of chunking up our document and then using that to generate a synthetic data pair. All right, let's speed up through the rest of this. So it's going to loop through the rest of the data chunks and generate more instruction pairs. Now, again, feel free to sub in your own data here and see what it generates, because you'll then be able to use that for training. Now, we've got a little bit of a problem. You see, when we went and dumped out our data, we had something that looks like this. Now, this might not look like much, but if we go and format this document, take a look. We've got each chunk represented as its own segment of instruction pairs. So we've got 0, we've got 1, 2, and each one of these instruction pairs references a specific chunk. We really just need this question and answer formatted inside of our dictionary that we're going to pass through as our training data. So how do we fix this? Foreshadowing and drama aside, we can just go on ahead and create another pre-processing function to go and clean this up. So I'm going to create a new file called pre-processing. And then what we're going to go on ahead and do is just fix it up. So I'm going to create a function which takes in our JSON data set and processes it out into a nicely processed file. So we're going to open up our tm1data.json file that you can see right here. And what we're going to do is we're going to loop through each one of those records. And by looping through each one of those records, we're going to be looping through each chunk. So you can see that we're going to pass each one of those chunks right here. So for each pair, what we're going to do is we're going to take that out and we're going to append it to our instructions list that we've got up here. So we should end up with a nice clean list. So for each one of those pairs, we're going to append it to our instructions list. And then what we're going to do is we're just going to print it out so that it looks quite nice and we can see the result of our work. Now, once we've got all of that pre-processed, we're going to dump it out into a data folder and we are going to dump out the new file as instruction.json. So that will be processed there. And then the last thing is we'll reopen it so we can see the result of the pre-processing and we'll print it out. Now, if we go on ahead and run this, we should end up with a new folder created with a file called instruction.json. So let's go on ahead and run that. To run it, I'm going to run uv run preprocessing.py. And it looks like we've got a bit of an error. So no such file or directory. What we can do is quickly solve that by creating a new folder called data. And let's try running that again. Take a look. So we've now got our processed data set. So that's obviously gone quite quickly. If we take a look, you can see that we've got our file called instruction.json here. And if we go and format that document, you can see that we've now gone and processed it into a nicely formatted document that we can actually go and use for our training. But I've got one more trick up my sleeve. Remember, when we went and generated this data set, we used those chunks as context to be able to go and generate the instructions. I found appending those chunks as context inside the instructions tends to help our LoRA perform a little bit better. So let's go on ahead and do that. Turns out this might not have been the greatest idea, but you'll see towards the end when we come and improve performance. I'm going to unpack the question and answer pairs while we're looping through them. And then what I'm going to do is I'm going to create a new context pair here. But this time I'm going to create a formatted string and append the chunk itself as context and then pass through the question itself. Then we're going to have our answer over here. And rather than rendering out our regular pair, we're going to append our context pair to our instructions list. Now, if we go on ahead and run this, uv run preprocessing.py and go and take a look at our instruction data set. Let's go and format this again. Take a look. We've now got our context appended to each one of our question and answer pairs. So hopefully this helps boost performance. Now I've got all the data prepared and you can see that here. We've now got the instructions to give to our LLM. But take a look here. There's hundreds, if not thousands of rows that our LLM's gonna need to walk through. This is gonna take a ton of time to train without a GPU. So how exactly do we set a GPU up? This brings us to stage 3, SSHing into a run pod instance. Now, so far, everything that I've been doing has been done on my MacBook Pro, but because we're going to be training this, we ideally want a bit of a GPU. So I'm gonna go on ahead and transition our environment over to run pod. So over here, I'm inside of the run pod console. I'm gonna choose an RTX A5000, which has a bit of VRAM, 25 gigabytes to be precise, and I'm gonna deploy that pod. Now, what I'm going to do as soon as this pod has connected is I'm going to connect to it via SSH. That means that we'll still be able to code inside of VS Code. That's now initialized. You can see here that the connect button is now available. I'm going to select SSH and then choose the option which says SSH connected over TCP. And then inside of VS Code, I'm going to add that SSH host here. And then I'm going to connect to it by selecting connect there. And this is going to give us an environment inside of VS Code that allows us to utilize that GPU on RunPod. I'm going to change our root directory to operate out of the workspace directory as soon as we're connected. So you can see here that I'll open the folder and then choose workspace. And then what I'm going to do is copy over our data directory. So this contains our instruction data set. So we're going to need that for our training script. So if we copy that over from our local machine, then we're now going to have this available inside of our run pod environment. And the last thing that we want to do to be able to get set up is to install UV inside of our run pod machine. So I'm going to run pip install UV. And then I'm going to initialize a new project by running UV init. GPU is now up and running, but how do we get it processing our dataset before training? This brings us to step 4, mapping and batching the data. Time to build our training loop. So I'm going to create a new file called train.py, and this is going to contain our data loading as well as our training loop. All right, time to install some dependencies. We're going to bring in datasets, transformers, torch, bits and bytes, pef, TRL, and Ollama. This is going to help us with all of our training. I know I'm sort of drip feeding this to you, but all the code is going to be available on GitHub with the specific versions I used as well. But run this at the command line if you're running in real time. So the first thing that we want to go on ahead and do is load our data. So we're going to bring in load dataset from the Hugging Face datasets repository. And I'm also going to bring in Ollama because you know I like it. So let's do a test dataset load. So I'm going to create a new instance of our dataset and I'm specifically going to point it at our data folder. So this should hopefully open up this over here. Now, if we go and set our split equal to train, let's go on ahead and print out an example of our data set. So I'm just going to print out the second or third example in this case. Now, if we go on ahead and run this, we should get an example of our data set printed out in yellow. And take a look, we've got our example printed out. So what we now need to do is prepare this for instruction tuning. We ideally want to be able to use this LLM in a chat-based environment. So we actually need to take our instruction tuning dataset and get that into a chat template. So we're going to go on ahead and do that. We're going to create a new function called format chat template, and it's going to take in a batch of training data as well as the tokenizer. And then we're going to format this into a chat template, almost like a prompt template that you might have seen for other Llama models like this. So the first thing that I need to go on ahead and do is define a system prompt. So this is going to be our system prompt. And again, all this code is going to be available via GitHub below. Then we need the specific chat template. Now the Llama family of models uses a specific chat template. So we are going to apply that to our tokenizer. And you can see that here. A little bit complicated, but basically we're injecting our content, the role, as well as our assistant and final output. Then what we need to go on ahead and do is loop through each one of the samples in the batch. So we're going to create a set of samples and we're going to extract the questions from the batch and the answers from the batch. And then what we're going to do is loop through each one of those. So once we've got each individual question and answer, we're going to convert it into a set of JSON where we're going to append the role. So we're defining our system prompt and our role as system. We're then going to define our role as user, and this is going to take in our question. And then we're also going to have our role as assistant, and this will have the content as our answer. So you can see that we're starting to structure our prompt to follow a typical chat template. Then what we're going to do is we're going to apply our chat template that we've just defined above, and that's going to take in all of our JSON row that you can see here. And we'll append that back into our samples right over there. Then we're going to return this. So when we go and process this in real time, we're going to return the instruction, which is going to be the questions, the response, which is going to be the answers, and the text, which is going to be our samples. Now, although we're returning the instruction, the response, and the text, when we actually go and use the supervised fine-tuning trainer, by default, it's only going to use the text field. We've gone ahead and defined this huge chat template function, but how do we go ahead and use it? Or at least test out a sample to see what it looks like? Well, let's do exactly that. So first up, from transformers, I'm going to import auto tokenizer because that's going to allow us to use the tokenizer over here. And then we're going to begin processing our data set. First up, we need to define our base model, and this is eventually going to be the large language model that we're going to choose, or small language model in this case, because we're only going to be tuning Llama 3.2 1B, but it is still going to be extremely performant. Then what we want to do is load up the tokenizer. So from the auto tokenizer.from pre-trained method, we're going to go on ahead and load in our base model. We're going to trust remote code. This is going to allow us to download the tokenizer from the Hugging Face repository, and we'll also need to pass in our API key or our access token here because the Llama 3.2 1B model is a restricted or /gated model. Now, then what we're going to do is we're going to take our data set and we are going to map through it. And specifically, we're going to use our format chat template function, which we've already gone and defined. So to do that, we're going to use a lambda function, and the X here represents each batch, which remember contains our question and answer pairs. Then what we're going to do is we're going to apply the format chat template method, and we're going to pass through the batch as well as the tokenizer, hence why we went and loaded it. Then we're going to specify the number of processes that we want to use for multi-processing. If you have a huge data set, this is obviously going to help speed up the process. We're going to specify that we want our data set to be batched, and we're going to set our batch size to 10. Note, if you're using a smaller GPU, you might want to drop this down. Then we're going to print out an example. So we're going to use Ollama because, again, you know I like colored outputs, and we are going to print out the first example in our training data set and then reset our Ollama coloring. Now, let's go on ahead and run this. To run it, we can go to our terminal and we're going to run uv run train.py. And all things holding equal, we should be able to see an example of our transform dataset with the chat template applied. And take a look, we have our dataset now printed out. Now remember, this first segment over here is just our raw dataset, which is being loaded using the dataset's capability, which contains our question as well as our response. It should be somewhere in there, the answer right down here. Now, over here, this is after our chat template has been applied. Now, keep in mind when we go and use the supervised fine-tuning trainer, we're only going to be training on the text component. But over here, you can see that this is our transform data set with the chat template applied. Been a while to get here, but the data is now ready for training. So what's next? Stage 5, kicking off training. Now we want to bring in our model. Now we've already brought in our tokenizer that you can see here, but we need the model as well because that is what we are going to be fine-tuning using LoRA, or specifically QLoRA. So how do we go about doing that? Well, first thing, we need to go on ahead and bring in the auto model for causal LM class. And then right down here, we're going to begin bringing in our model. So we're going to create our model and we are going to load it from pre-trained. And remember, we already specified our base model over here. So we're going to bring that into this class as well. We're then going to specify what we want the model to run on. Now, because I'm running this on RunPod, I've got GPUs available, so we're going to run it on those GPUs. And then we are going to pass through our access token. Remember, this is a gated model, so we need to make sure that we pass that through. And then last but not least, we want to specify that we want to load it into our workspace. That way it's stored over here because this is where I've got disk space. You can choose where to save the model itself. Then we want to go on ahead and print it out. So I'm just going to show you what this model looks like because when it comes to quantizing it, you're going to see the difference. So let's print out the model. And I'm also going to print out the device that it's currently running on so that you can see that it is in fact running on a CUDA supported device. Now, if we go on ahead and run this by running uv run train.py, we should see our data being output, the template applied, and then we're going to see our model in and of itself, as well as the device in a few different colors, of course. Now, if you are running this for the first time, it may take a little while to download. It shouldn't be too long, but it's a relatively small model, but you are going to see that. All right, so we've got the orange text, that's our initial data set. The purple text, that's with our chat template applied. In a second, we should see the model. And take a look. So in light cyan, that is our model output there. So this is the representation of our Llama model. Now, if we quickly work our way down, you can see that we've got our embedding layer over here. We've also got our self-attention mechanisms, of which we have 16. We then have our multi-layer perceptron, or a fully connected layer, opening up over here. We've got our layer norm. We've got more layer norms. And then we have our rotary embedding, and finally our final language model output head. And right down here, you can see that it is in fact running on CUDA. But what if we wanted to quantize this? To do that, we need to start setting up our quantization config for our LLM. So what we're going to go on ahead and do is import the bits and bytes config, and we're also going to import torch. We're going to need this to specify the bfloat data type. Then if I scroll on down, we're going to begin building out our quantization config using that bits and bytes class. First up, we're going to specify that we want to load in our model in 4-bit. We're then going to specify that we want to use double quantization. This is going to save a little bit of memory again. We're also going to specify a quantization type as normal float 4 or NF4. And last but not least, we're going to specify our compute D type as torch bfloat 16. Then if we go on ahead and apply this quantization config to our model here, and then we go and run it again, this is why you'll see the difference. Keep in mind, take a look at these layers here. Now, if I go and rerun it, take a look, we've now got 4-bit linear layers. So we've got these layers over here, but if we scroll up, remember we previously just had non-quantized linear layers. Stretch, let's train this model. A lot of work for something which I probably could have just Googled, but that's fine. Let's go on ahead and fine tune this. So I'm gonna bring in a couple more dependencies. I'm gonna bring in the supervised fine tuning trainer, the SFT config from TRL, and I'm also going to bring in the LoRA config and prepare model for K-bit training. So this is going to get us ready for quantized training. So if I scroll on down, what I'm going to do is enable the model for gradient checkpointing. This is again going to save a bit of memory on our GPU, because remember we're only using one at the moment. And then I'm going to specify that I want to prepare the model for K-bit training. That is going to allow us to kick off quantized training. And then we are going to define our LoRA config. This is pretty important here. So we are going to specify our rank as 32. So a bigger rank means a bigger adapter, means bigger weights, but also means a slightly more performant adapter. And I'm going to set the alpha to 64. I think it's recommended to have this as a multiple or higher than the rank. So I've set it to 32 before and it's kind of worked. Setting it to 64 here, and we'll see how it actually performs. Then I'm going to set our LoRA dropout to 0.05. So this is going to be utilized during training. Should deactivate certain parameters to allow us to train a little bit better and perform better during inference. Okay, and then we're going to specify the target modules. I'm going to set this to all linear. So this is going to target our linear layers. Ideally, I think I'd probably try using the embedding layer in the future, but for now, we're going to set it to all linear and specify our task type as causal LM. We're then going to set up our trainer. So our trainer is going to be the supervised fine tuning trainer. We're going to pass through our model here. We're also going to specify that we want to use our training dataset, which we've already gone and pre-processed so lovingly. Then we're going to specify our arguments for our supervised fine tuning config. We're going to specify our output directory and the number of training epochs. Now, I've done a bunch of experiments here. I've set it to 50. You could train it for a little bit less, a little bit longer, but I found 50 works pretty well because we're going to scale out that data set as well. So the last thing that I need to do is pass through our LoRA config down here. Then all we need to do is tell the trainer to train. And then we're also going to save the model as well so that we've got these checkpoints saved when we want to go and deploy it using Ollama a little bit later. All right, there's nothing left to do but to train. So let's go and kick this off. So I'm going to clear our workspace and then run uv run train.py. Hopefully for the last time. All right, take a look. And our training's kicked off. Down the bottom, you can see that we are in fact training the model. Let's let it run. Now, model's trained, we don't need to run it on GPUs anymore. How can we get it running quickly, locally, like this? This brings us to stage 6, deploying locally using Ollama. All right, and that is our model train. Now, if we open up our Explorer, you can see that we've got our complete checkpoint as well as the final model. Now, what we're going to want to go on ahead and do is get this adapter config.json and this safe tensors file, because that's what we're going to need to deploy. Now, for whatever reason, I can't seem to copy this from locally to over here. So what I'm going to do is I'm going to jump into RunPod, and then I'm going to connect via Jupyter Notebook. and download it through there. So inside of Jupyter, you can see that we've got the exact same repository as what I'm showing here. The only thing is, if I jump into this final model folder, I can right click and download the adapter or the JSON config and then the safe tensors file. So you can see those are downloading now. Now I'm going to chuck this back into a folder on our local machine now to actually run this locally inside of Ollama. So if I create a new folder and I'm just going to call it checkpoints and then go to my downloads folder, you can see that these are still, looks like they might have finished downloading. Yep, so we can grab those and I'm going to throw them inside of this checkpoints folder. And let's get rid of the 6. And now we can begin deploying it using Ollama. Right, so to get this running inside of Ollama, I need to create a new model file. And inside of this, we're going to include two things, the base model and the adapter file path. So remember, our base model is llama 3.21b. So we're going to say from llama 3.21b, and then we're going to specify that we want to pass through the adapter file path. So the cool thing about Ollama is that you can actually load directly from this safe tensors file. So I'm just going to copy the path to this file. And we don't need the path to this specific adapter, but we do need the file path for the main repository. So that is our model file now created. Now to get this running inside of Ollama, we can open up a terminal. And remember, we're running locally now, not on RunPod. I can pass through the command Ollama create, and then the name of what I want my new LLM to be called. So I'm going to call it TM1 Bud. And then we want to pass through the file or file path to our model file. So I'm going to pass through -f model file, but you can also run it without passing through the file path if you're running this command from where the model file is created. For now, I'm just going to be explicit and pass through that model file. And look, success. That should effectively mean that we've got our new trained adapter running inside of Ollama. If I clear this and run Ollama list, take a look. We've got TM1 Bud running, and you can see it was modified 18 seconds ago. We're now deployed. So how do we go about actually testing to see what performance looks like? Well, to run TM1 Bud, remember, if we go and run Ollama list, we've got TM1 Bud running there. To actually run it, we can run Ollama run TM1 Bud, and that is our fine-tuned LLM now up and running. Now, I've got a couple of test samples here so we can take a look at what performance looks like, at least at a baseline. So over here, we've got our first question. What is the default behavior? Let's make this a little bit bigger. What is the default behavior of TM1 regarding kube loading on server startup? If I copy that, paste it in, take a look. So in TM1, when a cube is loaded on a server during server startup, the default behavior is to cache the cube's data in memory. This means the cube's data will be stored locally on the server and then retrieved from memory as needed. Take a look. That looks pretty good because considering our answer over here is a default TM1 loads all cubes into memory when a server starts, we've got the correct answer. What about this question? How does setting certain cubes to load on demand affect resource consumption? Let's take a look. So we've got increased database queries. That's not too great. Memory usage is correct. So we've effectively got the ability to not have to load everything on startup. So really it's all about faster server startup time. So it's not too bad. Now, the biggest question that I had is how is it going to perform on this question that we asked initially? What is the minimum number of dimensions for a cube specifically in IBM Cognos TM1? Actually, we didn't have specifically before. Let's remove that. So let's give that a crack. If we copy this and paste that over here, take a look. So we've now got the correct answer. In IBM Cognos TM1, the minimum number of dimensions required to create a cube is 2. So it's actually performing pretty well. But if we go and run this again, you can see that we're getting the response 3. And if we run it again, we've got 2. So it's performing better, but it isn't necessarily perfect. Right, so one of the things that I picked up a little bit later on is that when you go and run it directly within Ollama, so Ollama run TM1 Bud, you're not able to go and select greedy decoding without going and hard coding it inside of the model files. But we can do that within Langflow. So keep in mind that because we are running an Ollama node here, I can actually just go to my model name and then go and change it to TM1 Bud, which you can see right there. So if I go and choose that model, then we can actually go and run through our baseline prompts. And keep in mind, I've got tep k equal to 1, which effectively means that we're going to be running using greedy decoding. So we're going to be selecting the next most probable token. So a little bit less random or stochastic. So if we now go and hit the playground, we've got our prompts up here. Let's make this a little bit bigger, shall we? That's a bit better. Okay, so if we go and create a new chat, let's run through our baseline prompt. So first one, what is a pick list in IBM TM1? How'd we go here? Okay, so in transaction modeling, a pick list is a type of data element that stores the list of possible values. That's not bad. Pick lists are used to create custom forms, reports, business rules. That looks pretty good. All right, so what is so our critical one? What is the minimum number of dimensions? Let's try that. Remember, we had that massive hallucination. All right, take a look. In three-dimensional layout, TM1, a cube typically requires at least 3 dimensions to be placed correctly. So now we've got even probably like worse hallucinations after going and doing that fine-tuning. But we will fix it up. So not all that great there. In TM1, how do I create a dimension? I think this is the one that went and started talking about dynamics, 365. How'd we go here? All right, doesn't look like it's doing it. In IBM Cognos TM1, creating a dimension involves several steps. Open the model or workspace. Not quite. Click on objects or elements. That's still a bit of a hallucination. So this is all to be, or I guess that the focus here is opening up dimension editor and making an adjustment there. And then what was our last one? Again, this one's a little bit airy-fairy. So what are the core advantages of TM1? Real-time analytics, business rules engine. That is actually pretty accurate. Multi-dimensionality, that's pretty good. Data viz, yep. Performance optimization. Does it mention anything about being in memory? I don't know. You guys let me know in the comments below. But okay, so we're slightly better. I think maybe even a little bit worse, but we are going to improve performance. So how might we go about doing that? So if we take a look here, performance still isn't quite that great. How do we improve it to get it to perform more like this? Well, we're in the end game. Stage 7, improving performance. Okay, so I'm quickly going to go through what I found helped improve performance. Increasing the rank and alpha of the LoRA helped improve the performance of the LLM dramatically. The final parameters that I had are shown now. Adding more data also helped perform well, but it really depended on the quality of data. Having less generic data, but having ultra-targeted data also tended to perform really, really well. But I don't know how feasible this is when deploying a LLM into production. I tested simply 3 examples saying that a cube requires 2 dimensions and trained it for 20 epochs, but this potentially leads to overfitting and potentially even catastrophic forgetting. The 4th thing that I did was I improved the data quality using a data classification script. I'm going to show you this in a second and we're going to go through it. Way more performance. Still hallucinates occasionally, but when I combined it with more epochs as well, it tended to perform really, really well. Then if I went through data quality and specifically looked at the stuff that didn't perform so well and made sure that I had enough epochs, that combination tended to give me a pretty good LoRA. When it comes to the training parameters that I changed, I went and bumped up the rank to 256 here. I increased the LoRA to 512, so quite a significant increase, which meant that we'd have more parameters to be able to train and accept our knowledge. I found from Sebastian's post that you can see here that he recommends having alpha as double the rank. I found that this seems to be the standard practice in the industry, so I've gone and bumped that up as well. I also bumped up the number of training epochs all the way up to 100 epochs. Now, in all honesty, I also bumped this up to 500 epochs at one point just to see what performance would look like, and it definitely did boost performance, but it ended up meaning that I would need to train the LoRA for a few hours. So if you've got the time, recommend bumping up the number of epochs, or if you go and test this out and you've got a low performing LoRA, you might want to bump up the number of training epochs. The other thing that I also did because I went and trained for so long was I increased the number of save steps up to 1,000. This basically meant that rather than saving every 500 steps, I'd be saving every 1,000, which basically meant that when I went and saved these checkpoints, I was saving at a less frequent interval, because what happened originally was I actually went and used up all the disk space on the run pod instance that I was running, which meant that the training actually stopped before I finished the full number of epochs. So bumping that up would just save you a little bit of disk space, means that you don't need to increase the capacity on the run pod instance. But those were the final set of parameters that I had for the SFT trainer. Keep in mind, again, you can bump this up higher. I did at one point, and maybe I'll add those checkpoints into the GitHub repo if you want to see the performance on those. But I found that 100 seemed to get us a pretty well-performing LoRA. The next thing that I went and did is I actually deleted the context from the instruction tuning pair. So that meant just deleting this section here from our pre-processing component. So effectively, we would now just be outputting the question and the answer. So our data set ended up looking like this with our context sections and converted to something like this, where we purely just had the question and answer pair. I found that reducing the quantity of data but increasing the quality of data increased the performance significantly. And this is one of the first steps that I took but it's not the last one. So I had this idea that I could take the data that you can see here, but pass it through an LLM again. The only difference this time is that I would get this LLM to classify that particular instruction example in terms of accuracy and style. And really, I was taking a look to see whether or not the answer was self-contained and whether or not it accurately reflected a factual instruction. So what we're going to do is build up that data quality filter. So I'm going to create a new file and I'm going to call it data quality. And this is just locally, right? We don't need GPUs for this. So we're going to go data quality.py. The first thing that we're going to do inside of our data quality.py file is bring in a couple of things. We're going to bring in JSON base model from Pydantic. We're also going to bring in the completion endpoint from LLM so we can use our LLM. And while we're at it, we're going to bring in Ollama to get some stuff printing out to the terminal, which looks a little bit more clear. Then we're going to define two types. The first one is going to be a score, and this is going to be a class which we're effectively going to use to determine what our output should look like. So I'm going to have two different types of filters, one for accuracy or performance and another one for style. Each one of those scores is going to contain a score, so a numeric number, but also an explanation. Then in terms of what our rank is, we're going to get back the accuracy or whether or not it's a valid answer. And we're also going to get back style. And again, you could tune these or change them to sort of what you want, play around if you want to focus on your instruction tuning pair getting different types of output, but I found that this works pretty well. Then we're going to define a function, and this function is going to be our LLM call. It's going to take in one example record and it's going to return a dictionary, and that dictionary is going to be a dictionary which contains our rank, which will have accuracy and style, and accuracy and style will each have keys, score, and explanation. So that's sort of how these classes build into this. And we're going to do that by using the format method inside of our completion endpoint. Remember, we did this when we were actually generating the data set itself. So let's go on about generating that data set or generating our classification. So we're going to create a new stream and we're going to use the completion. We're then going to set our model equal to Qwen 2.5 14B. I actually had a thought that maybe I should use a different model here, but I found that using the same one tend to perform pretty well, but you could try a different one here. Maybe use Llama 3, maybe use Llama 4 if you've got an endpoint, but test that out. Okay, then we actually need our prompt template. So we're going to create a message endpoint. The role is going to be user. The actual prompt itself is going to be contained within the content key. And then this is the most important bit here. It's where we define what we tell our LLM to do and how to classify our instruction tuning pair. So here we're going to specify that we want to classify this instruction tuning record between 1 to 10 in terms of accuracy and style. And remember, we define those up here. We want to provide explanations for each one of those. So if we want to come back to take a look at why it generated a 1 to 10, we've got a bit of an explanation as well. The answer should be completely self-contained. If the question is not in fact a question, it should receive 0 for accuracy. So we don't just want blanket statements. We actually want a question or a prompt. If the answer does not adequately answer the question, it should receive a 1. Now keep in mind that I've put 0 here. I really should have put 1, but I'm showing you exactly what I did. Ideally, probably go and adjust this prompt because it's not quite that right, but that's fine. It's okay. So if the answer does not adequately answer the question, it should receive a 1 for accuracy. And if the question or answer are in any way harmful, not helpful, or honest, it should be classified as a 1 for style. So we're penalizing the instruction pair if it's not all that great. Now, if the question or answer are blank or a set of ellipses or full stop, full stop, full stop, return 1 for both. Again, we want to make sure that we get good responses back. Then we actually want to pass through the record. So we're going to pass through the record there and we want it to return as JSON, even though we're going to use a specific prompt template or prompt format out of this. Okay, and then we're going to set stream equal to true so we can see it in real time. We're going to set a couple of options. The number of predictions, we're going to set that to 2,000 tokens. The temperature is going to be 0.2. We also want to pass through our format. So remember, we want to pass through rank, which we went and defined up here. So we're going to get accuracy and style back as keys, and each one of those is going to have a score and explanation. Okay, that's looking good. So what we now need to do is actually go and pass through the stream. So you've seen this before. So we're just going to loop through each one of those components. We're going to extract the delta and we are going to print that out to the screen in light blue using Ollama. So we're going to print out the delta and then we're going to append that to our data string up there from over here. So that way we've got a way that we can export this if we need to as well, which we will a little bit later. So we're going to then pass it as JSON and return that back. Now, if it comes to running this, again, we're going to say if name is equal to main, let's create a test record. So our test record is going to be something like this. So we're going to have a question, and that question is going to be, what are cubes in TM1 used for? And our answer is going to be cubes in TM1 business analytics data with, or cubes in TM1 store business analytics data with each cell containing a measure being tracked. Then we want to take that test record and pass it through to our LLM call. Then if we go on ahead and run this, we're going to run uv run data quality.py. And fingers crossed, we should get Ollama printing it out in blue, and we'll actually see a score for our test record. And take a look, we're beginning to generate. So we've got our accuracy and we've got our style. So you can see for that particular example record, our accuracy has a score and it has an explanation. The score for accuracy is 7. The explanation is the answer provides a basic definition of what cubes are used for in TM1, but lacks detail about the functionality, versatility of cubes, which is crucial in business intelligence applications. If we take a look at our style, we've got a score of 8. The explanation being the response is clear and direct. However, it could benefit from more depth or examples to enhance the understanding and usefulness. How do we go about running this on our entire instruction tuning data set now? First up, what I'm going to go ahead and do is delete all of this. And then what we're going to do is we're going to create two lists, one called quality and one called instruction. So the only difference is that inside of our quality list, I'm going to store the classification results. So if we wanted to come back and have a look at why we got a certain score for a certain instruction pair, we'll be able to go on ahead and do that. Then what I'm going to do is I'm going to open up the existing instruction JSON document. Remember this one over here, this is without context. And we are going to loop through each one of those instructions. Now, remember when we go and set up our LLM call, all we need to do is pass through each one of those instructions to our LLM and it will generate the result. So if we go on ahead and do that, so we're going to loop through each one of those pairs. We're going to print it out first in yellow so we can see the instruction pair. And then we're going to go on ahead and send it to our LLM process, which should give us our classification from over here. Then we're going to go on ahead and double check our result. Now, if our accuracy is greater than equal to 6 and our style is greater than equal to 6, we're going to keep that instruction pair. If it's below that, we're not going to keep it. We're going to discard it and not use it for training. Because remember what I said, the quality of data is so critical when it comes to getting good performing LoRAs. So we're going to do that and we're going to append it to our instruction dataset. And keep in mind, our instruction dataset does not have our result appended to it. So we're going to append purely the example that has gone and passed muster to that instructions list. But we also want to keep the quality result as well. So I'm going to go to my quality list and I'm going to unpack the pair, but I'm also going to append the quality dictionary to that as well. So our result from our LLM is going to be put down here. And then we're going to dump both of those out. So we're just going to dump out two JSON dictionaries. So we're going to dump out one called instruction quality. So this is going to be our instruction pair result. So it's going to be the pairs, but without the classifications attached. So you'll see that there. So you can see that our instructions, keep in mind, those are the ones without the quality results. They're going down here. And then we're going to do the exact same, but we're going to dump out our quality results. So these are the ones with the classifications into another JSON file. So quality results are JSON. We'll have our classification results with all the explanations and all of that other good stuff. So let's go on ahead and do that, and we can now save this. Now, if we go on ahead and run this, so keep in mind, if we go and take a look at our data set, right now we've got instructions with context, and we don't have our quality result. If we go and run this though, we should get our quality results pushed out as well as our filtered instruction pairs. So we can run, let's make sure we've got this saved. So over here, it doesn't look like a save. That should look fine. We can go uv run data quality.py, and this should loop through each one of our instruction pairs. So that's our first example. So what is the primary purpose of chapter 2 in IBM Cognos TM1 documentation? And we've got our answer there. And you can see that we are now generating a result. So we've got a score of 3 and a style of 5. You can see that there. Looks like that one probably won't make it into the final data set. We've got our next one, 7 and 8. So this is going to go on and filter through all of our data sets. So that's now finished running. If we go and take a look, you can see I've got quality results.json here. If we format that document, you can see that we have our question, our answer, quality, and our stars. So we've got the classification results as well. If we go and take a look under data, I've now got the instruction quality.json file, and this is just our filtered data set. If I go all the way to the bottom, looks like we've got 1,078 lines. Remember, the instructions that we had prior to filtering went down to 2006. So we've clearly filtered down a lot of subpar instruction pairs. Now, what I'm going to go on ahead and do is take our instruction quality data set, throw that up onto our run pod instance and retrain. To do that, all I need to do is grab our instruction quality.json file, jump on over into my run pod instance and paste it over here. So this should now be under our data folder. Remember, our training script will just look at our data folder. It doesn't necessarily matter what is under there. So what we need to do is we need to delete our old instruction pair because we don't want this. This is the one that still has the context. So I'm going to right click and delete that. And remember, we've already gone and updated our parameters in our train file. We've got our updated rank and our updated LoRA alpha. So all that's left to do is kick off the training run again. So I can go uv run train.py, and this should kick off successfully. And now use our updated data set. In a sec, we should see our GPU spin up on run pod. Let's give that a second. Okay, so you can see that we've gone and loaded in our data. So over here, we've got our unprocessed data set, and down here, we've got our post-processed data set. And keep in mind, you can see that we haven't gone and appended the context to the question. So we can see that our changes have been applied. And in a second, you can see the training run has also kicked off. So right down here, we can see that we are now running. Looks like it's going to take roughly 48 minutes, 47 minutes. We'll come back once that's done. Okay, so that is our LoRA trained. So you can see that our final training loss was 0.55. The number of tokens it saw was 3.171 million. The mean token accuracy was 0.95. So ideally you want training loss to be lower, mean token accuracy to be higher, and number of tokens, obviously that depends on how many epochs you run, as well as the size of your data set. So how do we go about deploying this now? Well, what we can go on ahead and do is grab our complete checkpoint. So you can see that those are now available. We've also got all of the checkpoints that have been saved every 1,000 steps. And again, remember, if you go and train it for 500 epochs, you're gonna have way more checkpoints down here. Okay, so what we are going to do now though is download these checkpoints. Now I'm just gonna do it via Jupyter again. So I'm just going to open up Jupyter Lab. Right, so I'm in Run Pod again. I can go to connect, and then you can see over here, I've got Jupyter Lab ready. So if I open that up, this should mimic the environment that we've trained our LLM in. Perfect. All right, so I'm just gonna go to complete checkpoint. And then what I'm gonna do is I'm gonna grab the config. So we're just gonna right click that and hit download. And then I'm gonna grab the adapter and download that as well. So the adapter is what? Let's double check, is 688 megabytes in size. Okay, let's let that download and then we're gonna deploy it via Ollama. So that's our config and our safe tensors file now downloaded. So it looks like it's 721 megs once it goes and downloads. So I'm going to copy this over. And then what I'm going to do is I'm going to jump back into my local instance. So you can see right up here, this is my local instance. If I jump on over, you can see that this is the SSH instance over here. So what I'm going to do is I'm going to open up our Explorer, and then under the checkpoints folder, I'm going to paste those two new files in. So we're effectively going to be overriding the configs that we've got here. I'm going to get rid of the old safe tensors files. We don't need those for now. And then what I'm going to do is I'm going to delete the numbers off them, because remember, inside of our model file, it's going to be looking for the adapter config and the adapter model.safetensors file. This doesn't need to change over here. What we do need to do though is make sure that we give it a unique name, because if I go and run Ollama list, I've got quite a few tier 1 byte experiments. You can see if I scroll on up, I've got all of these over here. Obviously, it's been quite a fair bit of experimentation to try to get this running, but I wanted a really complete tutorial for you guys. So We're going to call it, let's keep it really simple, TM1bud-100 because we trained it for 100 epochs. Oh, we've got this one over here. Now let's just call it TM1bud-100. Okay, so let's go and create this. So to run it, we can go and run, or to create it, I'm going to run Ollama create TM1bud-100. And if we go and run this, so this is going to pick up our model file because we're currently operating in the same directory as the model file. And it should pick up our new safe tensors file. So if I now go and run Ollama list, we should have our TM1bud-100. Take a look, TM1bud-100 latest. So that is now deployed via Ollama. Now, if we go back on over to Langflow and refresh our model names, we should be able to pick up TM1bud-100 and take a look. It's our first instance there. You can see all of the other ones that I've gone and deployed previously. If I go and choose TM1bud-100, we should now effectively be running our latest model. Now, if we go and open up our playground, let's test it out. So remember, we had some positive results and maybe some not so great results. So remember our first baseline question, what is a pick list in TM1? Let's paste that in. Let's make this a little bit bigger. So in TM1, a pick list is a type of element that can be used to store and manage values. It's essentially a drop-down menu that is perfect. Okay, so what about the biggie? What is the minimum number of dimensions in TM1? Take a look. In TM1, a cube requires at least 2 dimensions, so we are bang on for that. What about our third question? In TM1, how do I create a dimension? Remember, we're looking for something along the lines of opening up a dimension editor, so on and so forth. How did we go there? Take a look. So to create a dimension in TM1, follow these steps. Look, you can also use the dimension editor. So we are definitely coming through. So the dimension option, create a dimension, create a dialog box. That's looking pretty good. So we're already looking significantly better. What are the advantages of TM1? I don't know if we've actually put this in the data set. So let's see how it actually performs. Single source of truth, that's bang on. Improved data integrity. So again, we do have validation rules and checks in it. Enhanced business intelligence, that's great. Simplified downtime, increased security. These advantages are an essential tool. Nothing in terms of memory. But again, keep in mind, we'd probably need to check the data set to see whether or not we've actually banged that in. But this is actually so much better, right? Consider how we performed initially. We weren't really getting a pick list. Oh, we were getting a pick list, but the number of dimensions was completely blown out. To create a dimension was talking about Dynamics 365. So this is obviously significantly better compared to what we initially had. And keep in mind, you can go and change out this data set and go and train it on exactly what you want. All you need to do is go and change the PDF that we're looking at and then change the docling pickup so that it goes and chunks out your data set. But that, in a nutshell, is how to go about fine-tuning a large language model using LoRA.